was it okay? It's okay, then I go without, because I don't like this at all. I will try a little higher. Yeah, okay, good. Okay, good morning. Yesterday I told you a little bit about interfacial stress distribution, and this presentation will be instead about the separation between the surfaces and some applications of that. First I will tell you about how you can calculate the average separation when you use together two elastic solids with raft surfaces. And I will show you a very simple experimental test done by my PhD student. And then I will tell you about how you can calculate the distribution of interfacial separation, not just the average value. And then I will give you an application to literature of fields. So here we assume you have a randomly rough, hard substrate. And we squeeze an elastic block with a flat surface against this hard substrate. And when we apply the pressure up here, what will happen is that the bottom surface of the block here will start to penetrate into this roughness. And the only thing which is stopping from penetrating into is the fact that you will build up elastic energy in each of these contact regions. And one can show rather easily that to apply an average pressure up here, you have something which is like Newton's equation almost, or the pressure here is given by the derivative of the interfacial energy stored up here, the elastic energy stored up here, per unit area, derivative with respect to this separation here. So it's like the force equal to the derivative of potential energy. And this equation is exact. And yesterday I told you that if you bring the elastic solid in contact with a hard substrate like this, the area of contact is proportional to the normal load, at least for a strong applied normal load. And from that you can deduce that the amount of elastic energy stored up here is also proportional to the normal load, because it's determined by the area of contact. So if you look at the stored up elastic energy per unit area, it will be given by the normal force per unit area, which is this applied pressure. And if you combine these two equations here, you get an equation which is trivial to solve, and it tells you that the applied pressure will be related to this interfacial separation via this exponential law here. And U0 is some characteristic length, which turns out to be of order that we can square up here. And the full theory I have an explicit expression for this, so I can calculate U0. Determined basically by the power spectra of this rough surface. So this is almost trivial theory, which was worked out only rather recently, and very quickly we did an experiment to test this. And this experiment done by Prof, which is sitting in the audience here. And we did the following experiment. We took a silicon rubber block, cylindrical block. Here we have a steel surface. Here we have a randomly rough surface. We apply some normal force here that will make the block of the steel surface move downwards here as a result of two things. Then we will compress this block, we will get a little thinner, and the bottom surface of the block will start to penetrate into the roughness profile. And we are really interested in this penetration. And that means that we have to subtract away from this downward movement here, we have to subtract away the compression of the block. And so this exponential relation I showed you before, we will take a logarithm on that, here basically the applied pressure. You get the equation which looks like this. Logarithm of applied pressure is basically linearly related to this penetration here, which is given by the movement of the upper surface minus the compression of the rubber block, which is this last step. This simple formula is only valid if you have, for this compression, it's only valid if you have lubricated surfaces here, so the block can slip relative to the surfaces. Otherwise, the block will deform in a different way, and we get displacement of this surface outwards here, but this edge is fixed. And in that case, we can still use this formula, but we need to put in an effective elasticity here, which is higher than it is if you have lubricated surface. This is some pictures from the experiment done by Lawrence. We had an asphalt core surface. This is the upper steel surface. This is a silicon rubber block. This is before contact. This is a very small contact load. You can see only a few contact spots. This is a little bigger contact, and here we're almost squeezed into contact. Almost squeezed into complete contact with the rock surface. Here I plot the experimental result and the theory prediction. This is this penetration in millimeter, and this is the logarithm of the pipe ratio in units of elastic maneuvers. The green line is the theory prediction, and the red the blue line of the message data. The experiment was repeated twice, that's why you have two curves. And you can see it's very good agreement between calculation and experiment. So this fit there's no fitting parameters here. We're measuring separating the elastic modules, and we're measuring the power spectrum. We obtain that we fit without any fitting parameter. There's only some deviation at very low applied pressures. And in fact, this experimental curve will start to go down here. And that's because the experiment is for a finite system, while the theory is for an infinite system. For an infinite system, you have basically a sample of infinite high asperities, which means that you will always make contact. In the experiment, of course, you have a finite height of the highest asperity, and if the separation is larger than that, then the applied pressure here must be equal to zero. So this deviation is a finite size effect, which is what I understand theoretically. This curve shows just again the calculated relation between interfacial separation and the pressure. And the curve I showed you before was the asymptotic result, this dashed line here, where you have exponential relation between these two quantities, A and U. And the full line here is the full calculation when I use, so it's a linear calculation, not asymptotic result. And here you can see that you start to deviate from this asymptotic relation when you reach very small separation or very large squeezing pressures. And in fact, you need hardly pressure in order to squeeze into perfect contact. And in principle, you need almost infinite pressures in order to reach into perfect contact because you will see to zero. And this is a theory prediction. Also, when you look at higher pressures, the experiment was only this line here where you are in the linear relation between these two quantities. You can also include adhesion in this theory. So this figure shows again the logarithm of the squeezing pressure as function of interfacial separation. This is without adhesion. And here is some calculation we did with including adhesion. And this squares here is result of molecular dynamics calculation using a small system solving the problem with Lennard-Johnson interaction acting between the surfaces. And this is a theory prediction. You can see it's very good agreement with the numerical simulation. In addition, you can see that if you bring at a particular pressure here, say 10-6 here, when you include the adhesion, when you increase the adhesion, the interfacial separation gets smaller and smaller. And that's because, of course, the attraction between the surfaces will pull them into closer contact than you would have if you have no adhesion included. And the stronger you make the Lennard-Johnson interaction, calculus by this parameter here, the more you pull it into contact. There has been no experimental test of that. Now, this what I told you now is was only about the average separation between the surfaces. I'm really interested of not just the average, but the distribution of interfacial separation. So here you have a large separation, here you have no separation. Or at least you think you have no separation here. This is how the interface looks like at particular magnification. If I would increase my magnification to the highest possible atomic resolution, say, then if I look at this reading here, where it looks like I have contact, it turns out I don't have complete contact, so I have some interfacial separation here too. And using my theory, I can calculate this quantity here. This is the average interfacial separation between the surfaces. In a region which appears to be contact when I look at the system of magnification separate. perfect separation between the surfaces here, because they are not really in complete contact anymore, so they are still separated by some distance. And this depends on the magnification. So if I lower the magnification, this will increase. And finally, I need one more quantity in order to complete things, and that is what I call the average separation. I call it, I wrote it by U1. It's defined in the following way. We look at the interface at a given magnification, which I call Z here. Now we slightly reduce magnification. Then we have a bigger contact area. So this island, this contact island, must grow. It's a little more complicated than I've indicated here, but they must grow in size. And U1 at this magnification set is the average separation between the surfaces in this big area. That's defined as U1, which was defined in the magnification. And based on that quantity, I can calculate, I derive an expression for the distribution of interfacial separations. It's an integral of magnification here. This is the derivative of the area of contact, function of magnification. It depends on the root mean square roughness observed at a given magnification, and it depends on this function U1. And this is very important quantity which I will use in some application later on. These figures show what we have done again in the near-term test. So the blue line is a result of a molecular dynamics calculation. This is the distribution of interfacial separation, expansion of the interfacial separation. This is a zero applied pressure. So basically we have just here is a rough surface, and the upper surface is just touching the highest of purity. And so we have this separation U here, which will vary on the surface, and it will have some distribution which, according to theory, should be a Gaussian if you run on the rough surface. And the blue line doesn't show exactly Gaussian because it's still a finite system, and in a small finite system you have always some fluctuation away from the theoretical expected result. Here we apply some finite squeezing pressure, which now means that this surface will move closer, maybe into contact in some places, and the average interfacial separation will decrease. And what will happen is that this distribution will go towards smaller separation. And the blue line again is a theory, and this is what I calculate. Excuse me, the red line is a theory, and the blue line is molecular dynamics result. And this is even higher pressure. And if you squeeze very, very hard, of course, everything will be piling up at zero. This is separation. Okay, this is my first application of this concept of interfacial separation. It's leak rate of seals. It's a very important topic in application. We have a fluid here under high pressure. We have a rubber, for example, it would be a rubber O-ring, which make contact with the substrate here. But in general, because of roughness, there will be some channels at the interface where fluid can leak from that side to that side. And here we have a low pressure fluid, so we'll have a flow of fluid at the interface from this side to that side. And that's called leakage of this seal. And this is a picture, again, based on this molecular dynamics calculation. It's basically an Excel result where we look at the interface between an elastic block with a flat surface and the running the rough, rigid substrate. When you look at this with different magnification now again, the low magnification, the surface appears smooth, and it looks like we're contact everywhere. To increase magnification, we start to observe some low wavelength roughness. We start to observe long contact radius, and you increase magnification even more and more. And suppose the contact will look like this, and we have high pressure fluid here, low pressure fluid here, and we ask, is there any channel for the fluid to move from this side to that side? Then you can look here that if you try to move, you will leak into this wall. You cannot go from that side to that side. There's no open channel which can take you from this side to that side. And not even here. Yeah, here we found the first open channel. You can go like that. And so what is happening here is that when we go from this magnification to that magnification, we finally observe a non-contact channel going from one side to another side. So the white area, the non-contact area, has calculated. So if you would look at the seal with an optical microscope, say at this magnification, you would say this seal does not leak because there is no open channel for the fluid to move from this side to that side. But if you this magnification, you will say, this seal will leak because now we have an open channel here. And if you increase magnification even more, you will find many more channels where the fluid can move from one side to the other side. However, if you want to calculate the leak rate of this seal, the most important thing is what's happening close to this population threshold, because here the channels are the widest and the separation between surfaces in the normal direction is the largest. So in the simplest theory of leak rate of this seal, you will just look at the system at this population threshold and you will find out what is the size of this most narrow junction. And then one assumes that, in the simplest theory, one assumes that all the pressure drop will go from that side to that side, happen over this smallest junction. Hence, because of viscosity of the fluid, will have a pressure drop when it flows through here, and you assume that that is sort of what limits the fluid flow. So we worked out that theory. And in order to calculate this leakage, you need, of course, now the separation between the surfaces in this most narrow constriction, and that was determined by the theory I showed you before. And the experiment which Lawrence did is very simple and very cheap. We have just a plexiglass cylinder about 1 meter high. We produce a rubber seal here of silicon rubber with a rectangular cross section, which we put down here. And here we have a rough surface with sandpaper or sandblasted plexiglass or something like that. And then we just look how the fill it with water, we just look how this height increases function of time. And that gives you the leakage out to the interface. And we can do that for different contact pressure here by changing the load, which we have up here. Here I plotted the leak rate, logarithm of the leak rate, with cubic centimeter per second, as function of the squeezing pressure. The squeezing pressure, that's a nominal pressure which acts at the interface here. It comes because of the load. Yeah. The blue symbols is the measured data for the 3 different surfaces. One sandpaper surface and 2 sandblasted surfaces. And this was sandblasted longer time, so it has more roughness than this surface. And this theory I just told you about, which we call single junction theory, because in this theory, one single junction is the most important thing. It keeps the red line, and the green line is another theory, which in principle should be better, based on effective medium theory. I don't know if you know effective medium theory, but it has been used in a homogeneous system. It has been used often to calculate properties of a homogeneous system. But you see, there's no big difference in these 2 different theories. That makes us confident that already this single junction theory is very accurate. And as you can see, it's very good agreement with the experiment. This theory assumes that the surface is randomly rough. The randomly rough surface has a Gaussian height distribution. And not all real surfaces have a Gaussian height distribution. If you take sandpaper, for example, it looks much more like this. Because sandpaper is produced by adding some stones with very sharp edges, like this. And then they are glued to a paper, so you have a resin layer here. It typically looks like this. So you have rather smooth wedges, and you have these rather sharp things pointing up. And so this is not. This will not have a Gaussian height distribution. This will have a skew. This surface will have skewness. I cannot really pronounce it very well. But if you look at height distribution, it will have a tail extending to a higher radius than in the opposite direction. The relative probability height of the surface height is a function of the height. And so this skewness, which is defined by a moment like this of the height profile, for this sandpaper, it's almost a quarter of 1. For Gaussian surface, this will be equal to 0. So in principle, we cannot strictly apply our theory to this kind of system, but I will tell you that we can do it in an approximate way. what I want to illustrate with this figure here is that when you look at liquid of seals, you can expect a very big difference between this kind of roughness and this kind of roughness, which you obtain from here by just inverting this roughness profile. So what is right here, you can see that if you invert it, you will get this profile here. These two surfaces have the same power spectra, and they have the same Pugno square roughness. But you can imagine that when you block in contact here, you have much more empty volume here than you have here. So you expect much higher decay for this surface than for this surface. In my theory, if I apply it up into just straight forward, I would get the same leakage for both surfaces, which is clearly not the case. So what we are doing is we have used in our calculation not the power spectra of this surface or that surface, but which are the same, but we have used what we call the top power spectra when we calculate leakage. And top power spectra basically, you take your massive surface profile. Okay, I will take something which looks similar to a running or that. Take our massive surface profile, we put in the average plane, and then basically we assume that things below the average plane is the same as looks the same as above, and not like it actually looks, but it looks more like it looked above. That way you can find what we call the top power spectra. And here we've done calculation again. This is squeezing against the sandpaper, and then we get this message data, and this is a pure prediction. This is the top power spectra. Now we've done a second experiment. We took our sandpaper, which has this kind of surface hardness, and then we cross-linked silicon rubber against it, and then we remove it, and then we'll get a rubber surface which has the opposite roughness as the sandpaper, inverted roughness of the sandpaper, and then we put that in contact now with a smooth surface, not with a rough surface, but with a smooth surface. We have the same contact product as original, but with inverted roughness. And in that case, we expected smaller leakage. And as you can see here, this is a clear prediction using this top power spectra of the new inverted surface. And these are experimental data. You can see there's a large drop in the leakage just by inverting the surface profile. And here you can also start to see some deviation between theory and experiment. And we think this is due to adhesion. The adhesion will, because these tops are very smooth, the top here are very smooth of the inverted surface, they can become in adhesive contact with the substrate, and they will pull the surfaces into closer contact. So the leakage rate will drop below the value predicted by the theory. And this effect is larger on PMMA than on glass, because the attraction is stronger when you have a PMMA surface. This has to do with the wetting on the water as the fluid. And the effective interaction is higher with this surface than with that surface. Effective attraction. So we think we can also calculate leakage of seals which have not Gaussian random roughness but more complex roughness. So this figure, or this, here I want to just summarize the difference between the prediction of Williamson and what I predicted with my theory. I told you already that this theory I'm using predict an exponential relation between the squeezing pressure and the interfacial separation, at least for low squeezing pressures. If you're using Williamson theory, you get something which is more like a Gaussian. And you know that there's a huge difference between exponential and Gaussian. And they get a Gaussian simply because the height profile, the height distribution of heights is Gaussian on this random graph surface. You can also look at something which directly reflects long-range elastic coupling. This is a twin complement of the stress acting at the interface. This is sort of stress correlation function. And according to Greenwood-Williamson theory, it should scale with a wave vector from this way here. So this is the Gauss exponent related to the factor properties of the surface. According to my theory, it scales much weaker. Matter of fact, I don't have this factor 2 here. And there's been numerical simulation by Mark Robbins and Martin Mills and other people, and they find exactly this scaling here, not this scaling people like that. And finally, if you look at the contact area, I told you yesterday that Ringwald-Williamson theory predict almost linear dependence, but this is only for extremely small contact areas. I predict with my theory, as I showed you yesterday, that up to maybe 10% contact, so you have basically a linear relation. They predict, depending on how you treat the surface, depending on what radius you put for this smallest asperities, you will start to get deviation of very extremely small area from this approximately linear dependence. So this theory I've applied to many different problems. Elastic and viscoelastic contact mechanics, rubber friction I'll tell you a little about this afternoon. Elastic plastic contact mechanics I told you about yesterday. Adhesion, that's what I will tell you about now. Capillary adhesion, liquid seals I already told you about. Elastohydrodynamics at low sliding velocity, I will tell you about this afternoon. And fluid squeeze out between rough elastic surfaces. And thermal and electric contact resistance. So many very important problems can be attacked with this theory. So develop. Okay, this is this part.
How you perform the molecular dynamics simulation?
How I
mean,
perform?
Yeah, how you perform the simulation? Are two-dimensional or
no,
three-dimensional?
it's three-dimensional, but we have something we call a smart block model. So, because we have rather big system, and it would take a very long time if you treat each atom as a real atom. So we use a block. And so the atoms at the interface are treated as real atoms with a real lattice constant. And usually we put maybe a second layer of real atoms. And then we use a coarse-grained picture. So we put longer, we double, say, the distance between the atoms and make them more heavy and change the lattice, change the spring constant between them in such a way that you have still the same elastic properties. And we can do that several times. And if you do that, basically the number of atoms involved in the block will scale just as the number of atoms is blank there. But it will speed up the calculation a lot, because instead of n cubed, it goes like n squared. And you don't lose any this is basically like a set still, because if you have short wavelength roughness, it will only deformation field from that will only extend into the solid here by a distance given by the wavelength of the roughness. So it will only put, with respect to that, you need to have an atomistic structure here. But if you have a long wavelength roughness, like this, for example, it will extend deep into here, but the deformation field coming from such a long wavelength roughness will very slowly in space here. So you don't need to have atomistic restriction up here. It's enough to have coarse-grained picture. So basically we have an exact description of the elastic properties here with respect to contact mechanics, but the simple scale like n squared, not like n cubed. That allows us to go look at other big
so basically, as you increase the magnification, you increase also the number of atoms you use?
No. Magnification refers to the surface roughness. So, in the simulations, we generate, I told you yesterday, we generate our surfaces mathematically by adding up plane waves with random faces. And to get the surface which we use as particular magnification, we just limit this range of wave vectors to wave vectors which are smaller than something which is proportional to this magnification. And here we have the smallest K vector. So by limited So when we reach the highest magnification, we include all the wave vectors in the sum. Because a large wave vector gives you short wavelength roughness. So that's the way we can change. When we change magnification in the molecular dynamics calculation, what we're doing is that we just change the amount of roughness we include in the surface. So we have to generate, using unknown numbers, we have to generate many different surfaces. Then for each magnification, we use a different surface. We remove short wavelength roughness on the surface.
Okay, but for the capillarity stuff,
Yeah.
so still the size of the coarse grain is enough to resolve the motion of water or something like that?
I'm not sure what you're speaking about now. I mean, I didn't speak about capillarity here. Oh, thank you. I did not speak about capillarity here. Something else, some more questions, or I can continue? Okay. Oh, this I'm not sure because this is like the last question, the last thing. If somebody wants to look, this is basically how you can divide this distribution of interface and separation, but I will not go into that details. Okay, now I'm coming to some more applications: adhesion, capillary adhesion, and bioadhesion. And I will not go too much into detail about bioadhesion because I think Prof will tell you about that a lot. So the most fundamental adhesion problem, or the most well-defined adhesion problem, is a sphere in contact with a flat surface. And for that case, I told you yesterday, there is this very famous JKR vessel that the pull-off force proportional to the radius and proportional to the interface binding net and the unit area for smooth surfaces or flat surfaces. And the way this vessel is obtained is by minimizing the total energy, which consists of the elastic deformation energy. To make contact here, you need to deform the rubber ball. And then there is some binding energy at the interface, which has to do with this interaction between the surfaces. And that's proportional to the area. Now, if you have surface roughness, things get more complicated because now you will not only have this elastic deformation in a big volume element here because of the contact, but you will have a lot of elastic energy stored close to this experience here. If the longest wavelength roughness is small compared to the diameter of this contact region here, you can still use the JKR pull-off force equation. The only thing you have to do is that you need to produce an effective interface binding energy here. And that effective interface binding energy is defined here. So this effective interface binding energy times the nominal area would be pi r squared, r is the radius here. That's equal to the true binding energy, which comes from the area of contact. And with A here, you know, this area here, plus this area here, and so on. And now we're taking into account this the curved area, not just projected area, but the curved area. And delta gamma is the binding energy unit area in this region where you make atomic contact. And then you have to subtract away the elastic energy stored in this close to this aspirative. Because to make contact, you need to deform the rubber surface on the short wavelength scale here, and you store up a lot of elastic energy here, that's what I told you before. But this is an effective interface binding energy per unit area, and if you use it defined this way, you can still apply the JKR theory. And before telling you how to calculate this effective interface energy, let me show you some results. These are very classical experiments by Fuller and Tabo. Quite a long time ago. And they did an experiment on rubber balls, silicon rubber balls, in contact with rough surfaces. This was plexiglass surfaces, which was sandblasted. If you sandblast along with time, you get more roughness. And here they have plotted, basically this is pull-off force as a function of the root square roughness of the substrate. And here they use two different rubber, a little stiffer rubber. This is elastic modulus, 0.5 megapascal roughly, and here another rubber which is about 10 times softer. And you can see that for this stiffer rubber, already a few micrometers roughness make the adhesion disappear. And if you have a softer rubber, you have to go to larger wooden scrubbers before adhesion disappears. And the reason for that is that if you have a softer rubber, it costs much less energy to deform the rubber surface to make contact here. So this last term here, the score left energy becomes very small. And also the total contact area will become larger than it is in this case. If you look at the, yeah, compare this to different cases. So this problem again can be solved using my contact mechanics theory, which I described yesterday. There's only one difference. We need to change one boundary condition. Yesterday, we had, when we didn't include addition, we had a boundary condition that the probability distribution at zero stress vanish. But when you include addition, you can have tensile stress at interface. And you can introduce an additional stress here, which is a maximum tensile stress possible at interface. And when you reach that point, to the left of that point, this probability distribution will again vanish. So this is the maximum possible tensile stress at interface. And you can use a theorem of effects to argue that this maximum possible tensile stress is related to this effective vessel energy using this formula which I show you here. 1.5. It's called 1.5. Well, the last modulus, the effective vessel energy, and also the length scale coming here this way. This is just standard vessel theorem effect. So now you can solve this equation again with this initial condition here. And here I show you two examples. I have, in one case, I have a rather high elasticity material, 15 megapascal elasticity, and in the other case, I have a softer elastic material. So this, on this side, it's stiffer, and on this side, it's softer. And if you use a stiffer material, you have the top figure here shows the area of well contact. So this is the area at the highest magnification. And the green line is the result without adhesion. The red line is the result with adhesion. And you can see that including adhesion, in this case, still gives a linear relation between contact area and the applied normal load. But the slope is much higher than it is if you neglect adhesion. I will tell you in a moment for why it's still linear determinants there. This shows the area of contact of functional magnification, and the green curve is without adhesion, it's similar to what I showed you yesterday. The red curve is when you include adhesion. What happened now is that in the beginning, when you increase magnification, you don't see any influence of the adhesion. You just follow the green line here. And only when you reach some critical magnification will adhesion start to manifest itself. And now you can see when you reach the critical magnification, the contact area no longer drops, but it stays constant. Which means that when you increase magnification, the contact spots which you observe at this magnification, they don't become smaller, they don't split up into smaller regions. They just stay constant here. This shows this effective vessel energy, the functional magnification, and you have a behavior which looks like I've indicated here. The important thing here is that when you go to the lowest magnification, this quantity vanish. And the pull-off force, the gamma effective we have to use in this out theory is gamma effective as macroscopic length scale, so it's the lowest magnification here. So in this particular experiment, if you remove the rubber ball, you don't feel any attraction at all. So take our formula, we predict zero adhesion force. So in this case, adhesion only manifests itself as an increase in the contact area when you look at the system at large magnification. Here is the area at the highest magnification. If you make the rubber softer, then it turns out that you end up at the finite value here. That means that in this case, you will observe a pull-off force, which you did not do in this case. And if you look at, in this case, you look at the area of contact, it's no longer depends linearly on the applied load or applied pressure, but you end up at the finite value, which you expect, of course. If you have adhesion acting on macroscopic level, then there should be finite contact area even when the external load is zero. So what this shows that even if you don't detect any adhesion can still manifest itself. For example, if you do the sliding, sliding friction, what matters is the area of real contact, and the area of real contact is strongly enhanced here. So even if you cannot detect adhesion in the pull-off, it will still manifest itself in other experiments like the sliding friction. And this will just show you what I told you. Without adhesion, when you magnify contact radius, this magnification, then will almost break up into smaller contact radius. When you include adhesion, there will be critical magnification, and beyond that critical magnification, if you increase that magnification, the contact radius still looks exactly the same. While in the beginning, at low magnification, you don't notice adhesion, and things look exactly the same with or without adhesion. So adhesion only influences contact mechanics at high enough magnification in general. We have done some numerical simulations again to test this theory. It was done just the last few months. So here is one of the rough surfaces we have used. This is in nanometers, so this is a relatively smooth surface. This dimension is 1,000 angstrom or something like that, a little less. And then we bring an elastic block in contact with that, and this block has a flat substrate. And this block is of the type I told you before, with this smart block. This is the smart block description. And here we plot the effective interfacial binding energy now as function of the root mean square roughness of the surface. So this is gamma effective at the lowest magnification. The red line is what we calculate theoretically using my theory, and the blue line is what we obtain from the molecular dynamics simulation. And you can see qualitatively that it's the same, but from the molecular dynamics calculation we obtain an adhesion which extends to larger roughness than predicted by theory. But that's also what you expect, because we are looking at a small system, and the separation between surfaces is quite small, even in the non-contact region. And in the theory we have a contact interaction, so in the theory we only bind where we really make contact. But in the molecular dynamics calculation, because of the long-range nature of the Leonard-Jones interaction here, you will also get some attraction from this non-contact region. That also get pushed towards the substrate here. So in some sense, we have stronger attraction when we use the molecular dynamics calculation compared to the analytical theory, where we only bind where we make real contact. So this is really, this deviation you expect to see only for smooth surfaces and small systems. If you have a macroscopic system, in most regions you will have so large separation here that this long-range interaction basically doesn't act in those regions. And then you expect much less difference between theory and experiment than indicated here. But still, this kind of curve is just what we see in experimentally. So this theory I told you about, there might be some complications to it. And it comes in the following way. That I told you yesterday that removing an elastic solid from the substrate is best seen as interfacial crack propagation. So we pull off here, what will happen is that the crack edge here will propagate inwards. But now we have a rough surface here. And when you start to pull here, I told you yesterday you will have a stress singularity here, that the stress start to diverge here, become very large. And that means that also a little in front of it, you can start to get rather large tensile stress coming from the external load. And what can happen now is that some aspheric contact region in front of this crack here, they can detach. So if we increase this force now, in this aspheric contact region where this aspheric is particularly low, you can detach, and this is a rapid snapping motion, and you will get elastic waves emitted here. In other words, what I'm trying to say is that the energy to propagate this crack might contain contributions like this, which is not included in the theory, which I explained before. And some sense, they can act as a multiplicative factor to the value which I calculated using my theory. Things like that have been suggested in this paper by Kim, published recently. And I basically agree about it, but one needs to do more studies to find out what such evidence are. Good. Now I will tell a little about bioradiations, but rather quickly, because I think Bob will tell you a lot of details. So very briefly about the lizard and a little about the tree frog, because I think no one else will speak about tree frogs. And you already heard in the presentation from Dow, I think that van der Waals interaction is actually very strong on the microscopic scale, if you just can make use of it. So if you have one steel bar here with 1 square centimeters cross section, and you attach it to a flat ceiling here, and we assume perfectly flat surfaces, then we assume just the van der Waals interaction acting in the interface, no chemical bonding, just van der Waals interaction. Then in principle you could put a car, the weight of a car here, without breaking this bond. Of course, we know that that doesn't happen. I mean, when I put this in contact here, I can still separate them without feeling any attraction. And the reason for that is that you never break the bonds between these two materials uniformly. So in fact, even if you would prepare perfectly smooth surfaces here, you will start to get stress concentration at the edges here, and you will have crack propagated, starting, say here, propagated, and you will have stress concentration here, so you will not break the bonds uniformly. You will break them one by one, in some sense, at the crack edge here. And then you will propagate through, and you will break all the bonds. And in reality, you have always some surface roughness, and you will have defect. You have some non-contact region, which is already, in some sense, a crack. That's already the edges where you can get stress concentration. So, in fact, this never happened, but what it illustrates is that even the weakest force of interest in quantum physics is very strong on a microscopic scale. So if you just can make use of it, you can get strong bonding. And what the insects and lizards and tree frogs have been able to do is to make use of this very weak force, which is not weak on a microscopic scale. So I told you already that in order to get strong bonding, you need to have elastically soft material. You need to be able to deform the surface, bottom surface, to make as good contact as possible with the substrate and store up as little elastic energy as possible close to this sphere contact region. So you need elastically soft material, and if you take Scotch tape, which is usually used for adhesives, it has an elastic modulus of only about 10 to the 3 Pascal. But in nature, you don't have that kind of soft material to play with. You have this keratin like proteins with an elastic modulus which is 1,000,000 times more than for Scotch tape. So then you ask, how can you use such a very stiff material to deform the material and make contact at the rough interface? And not only to make contact, but there is some requirement where you show that you can load a lizard with 4 kilograms and it can still keep itself if everything is perfect. Flat surface, and the reason that you have this may only 30 grams heavy, the reason you have this overbinding sort of is that he doesn't need to attach to a perfectly smooth surface. He needs to run on a stone wool. The stone wool has a lot of roughness, and then you cannot transport it in anymore. So most theories actually which have studied bioradiation now, they have used flat surfaces. But I think these are almost academic studies, but in that case, rough surfaces. If you don't put in surface roughness, you will not be close to the end. So the experiment was not done like I indicated. The experiment was hanging one lizard in one tube on one glass sheet. They put a rucksack on him and they loaded the rucksack until he fell down. Now, so the way you can get strong adhesion using a stiff material, strong adhesion to rough surface using a stiff material is by building porous material or non-compact material. So this is one design possibility where you have a lot of holes inside. And even better is this fiber structure. And when you have a fiber structure, you can easily deform the fibers to make contact to a rough surface. And the most advanced organism, the lizard, insult and the spiders, they have this hierarchic structure. And in my opinion, the risk of the hierarchic structure is that real surfaces have surface roughness on many different length scales. So if you have long wavelength roughness to make contact here, you need rather long asperities, and you can just bend them a little to make contact here. But if each such long fiber here would end with a smooth curved surface here, you could still not bind here, because you have roughness at shorter length scale on top of this smooth disappeared, which looks smooth here. So if you magnify here, you observe new surface roughness, as I told you before,